All right, let's jump right into this explainer. Today, we're demystifying the complex math and architecture behind classical automatic speech recognition. We're going to break it all down step by step, starting with the foundational GMM-HMM models and working our way all the way through the complete Kaldi training pipeline. So whether you're prepping for a tough machine learning interview or you just want to deeply understand how machines literally learn to hear, you are definitely in the right place. Here is our roadmap for today. We'll kick things off with a math foundation, break apart the anatomy of an HMM, explore its GMM engine, figure out how to scale up our context, and finally, put the whole shebang together in the Kaldi pipeline. Okay, part one, the math foundation. Think about it. When a machine hears audio, its ultimate job is to find the most likely sequence of words. Thanks to Bayes' rule, we can actually split that massive task into two distinct models. First up is the acoustic model, which is the probability of the observation given the word. That basically asks, how likely is this specific audio given a specific word? Then we have the language model, the probability of the word. That one asks, how likely is this word sequence to be spoken in general conversation? Now there's a third piece to Bayes' equation, the probability of the observation itself. But here's the cool trick. We safely drop it. Why? Because it's just a constant across all candidate words. Computing it would literally require summing over every possible word sequence in existence, which is completely intractable. Oh, and one more thing. We do all of this in log space to avoid computational underflow. Moving on to part two, the anatomy of the HMM. An HMM is essentially built on 5 core components that work together to map hidden phoneme states to actual observed MFCC audio sequences. You've got your hidden states, your left-to-right transitions, and your emissions, which describe the actual audio features we observe. Add in your initial starting probabilities and, of course, the observations themselves, and you've got it. This 5-piece architecture is literally the backbone of classical speech recognition. Now, if you're prepping for an ML interview, pay attention, because this is a classic. To make this model actually work, we have to make 2 massive assumptions, the Markov property and observation independence. The Markov property assumes the next state depends only on the current state, completely ignoring all history. Observation independence assumes the current audio observation depends solely on the current state, ignoring any past audio. Are these simplifications? Absolutely. In fact, they technically violate how real continuous speech works, but they are entirely necessary because without them, exact mathematical inference would be impossible. So here's a crucial point. A phoneme isn't just one static freeze frame of sound. It evolves. It has internal acoustic dynamics. A phoneme typically plays out over about 100 milliseconds, and we model this using exactly 3 states. It starts in an onset state as the vocal formants move into position, glides into a steady middle state representing the true center of the sound, and finally transitions out during the offset state. Let's make this super concrete. Take the word cat. Broken down, that's 3 sounds, k, a, and t. Since each of those 3 phonemes requires 3 states, tracing the word gives us an exact 9-state left-to-right journey. If someone says cat and the audio is 300 milliseconds long, that translates to 30 individual frames of acoustic data. The system takes those 30 frames and figures out the absolute best way to align them across those 9 internal states. And that mapping, that's what gives us our recognized word and our forced alignment. Let's hit part 3, the engine, focusing on GMMs and core problems. Before we dig into the math, we really need to ask a practical question. How on earth do we handle the fact that the exact same phoneme sounds wildly different depending on the speaker, their gender, and their accent? Well, a single Gaussian distribution just doesn't cut it. It only fits one bump of data. If a man, a woman, and a child all say the same vowel, one bell curve simply won't capture it. So we use a Gaussian Mixture Model, or a GMM. By combining 16 to 32 separate bell curves together, we create this multimodal, fuzzy fingerprint of the audio vectors. It handles speaker variability perfectly. Plus, we use diagonal covariance instead of full covariance. Why? Because the math of our audio features is specifically designed to be decorrelated. This saves us massive amounts of computational power without sacrificing accuracy. Here's another interview tip. Commit these 3 canonical HMM problems to memory. Number 1 is evaluation, where we compute total likelihood using the forward algorithm. Number 2 is decoding, where we find the single most likely path using the Viterbi algorithm. And number 3 is learning, where we estimate our parameters from hidden data using the Baum-Welch algorithm. Think about the sharp contrast between evaluation and decoding. Both the forward and Viterbi algorithms share the exact same dynamic programming structure and the same time complexity. The real difference? The forward algorithm sums over all possible paths to find the total likelihood of the audio. The Viterbi algorithm maxes over the paths to decode the single best sequence of states. Summing gives you the whole picture, while maxing gives you the actual recognized speech. So, how do we actually teach this model? Our frame labels are technically hidden. We know the words that were spoken, but not exactly when each phoneme happened in the audio. To solve this, we bootstrap the learning process using Baum-Welch, which is literally an expectation maximization method. We start by initializing with a rough, uniform guess. Then, in the E step, we compute a soft alignment of frames to states. Over in the M step, we use those soft alignments to update and re-estimate our GMM parameters. We just iterate this over and over, monotonically improving our model until it finally converges. All right, part 4, scaling up context. We really have to ask why we abandoned simple, single-sound monophones. The answer is co-articulation. Because of the physical movements of our lips and tongue, the K sound in the word key sounds entirely different acoustically from the K sound in ka. To capture that reality, we can't just look at the sound in isolation. We have to look at the left and right context of every sound. We need triphones. To manage this context problem, we use something called a Senone. A Senone is essentially a clustered leaf on a phonetic decision tree. It intelligently groups together similar acoustic contexts so that they can share a single Gaussian mixture model. This decision tree clustering is basically magic. By asking targeted phonetic questions like, is the phoneme to the left a vowel, or is the phoneme to the right a stop, it takes an unmanageable 192,000 raw, mostly unseen triphone states and drastically shrinks them down to just 3,000 to 5,000 Senones. This is absolutely crucial because it guarantees every single Senone has enough training data to build a truly robust fingerprint. Finally, part 5, the Kaldi pipeline. The classic ASR flow is a strict linear progression. You literally cannot just skip to the end and build a complex model. You have to start at stage 1 with a flat start monophone model. From there, you build up to a basic triphone model in stage 2. Stages 3 and 4 introduce some pretty advanced data transformations. And only then, at stage 5, do you finally reach the complex neural network or chain models. What holds this entire pipeline together from stage to stage? Forced alignment. This is a critical process that uses that Viterbi algorithm we discussed earlier to map each exact audio frame to a specific hidden phoneme state. The monophone model generates an alignment to train the first triphone model. Then, that model generates an even better alignment to train the next one. Each stage is literally handing the subsequent stage the precise timing data it needs to learn. Okay, brace yourself for some alphabet soup. As you traverse stages try 2B and try 3B, you will inevitably encounter these transforms. To keep it super simple, LDA projects your features to maximize separation. But the biggest distinction to grasp here is between MLLT and FMLR. MLLT is a global rotation applied to all features to help our diagonal GMMs fit better. FMLR, though, is highly specific. It actively warps an individual speaker's unique features toward the average speaker space, perfectly compensating for different vocal tracks. Let's bring it all home with a quick 60-second summary. B's rule elegantly separates our acoustic and language models. Each phoneme operates as a 3-state left-to-right HMM to capture its internal sound dynamics. And the Gaussian Mixture Model steps in to handle the immense variability of human speech that a single bell curve just can't touch. If you understand these concepts, you understand the architecture that makes classical ASR possible. And that leaves us with one final provocative realization. In the age of deep learning, you might think all of this is just historical trivia. But honestly, these classical GMM-HMM models are absolutely not obsolete. They are a mandatory prerequisite. They generate the precise frame-level force alignments that modern neural networks strictly require in order to learn anything at all. Which begs the question, now that you've mastered the classical foundation, are you ready to take these forced alignments and build a true DNN-HMM hybrid? See you in the next explainer.